do it from my side. Yeah, so before jumping into the technical part, I would like to give some introduction about myself and about the committee. My name is Ali Selim. I am a fourth year PhD student at the University of Illinois, Chicago. I served as the past vice chair for the grad student test committee, which is operating under the WSDA of the EWRI group. So currently, our committee has 30 active members, and the objective of this committee is to connect graduate students, share job opportunities. We also hold bi-monthly technical and non-technical webinars just like this, and we meet in person annually at the EWRI conference. So we encourage all of you to join us to be updated about our webinars and job posting. You can join our mailing list through this link, or you can contact us by the email so that we add you to the mailing list. You can also follow up on LinkedIn. And it's also important to mention that all our webinars are recorded and you can access them through our YouTube channel. So I have to acknowledge all my colleagues who helped in preparing this webinar. I tried to include all of them, but maybe I missed someone. Meghna, Unmi, Nazia, Catalina, Saskia, Oscar, Toma, Camilo, and Ilyas, Wahba, Ilyas, Zausha. And of course, I have to also acknowledge our speakers today, Abby from Xylem, Kirk from Sandia National Lab, Jon from EBA. So we are very excited for this webinar specifically because the last time we checked, we had more than 100 participants. I'm not sure how many joined, but I'm sure some of them will be joining soon. In this webinar specifically, we have a variety of expertise. We have master's, PhD students, we have postdocs and professors, we have people from the industry and also from the utilities. So just to keep you informed, in this webinar, we will have three parts. In the first part, which will be for 35 minutes, we will be presenting PySWM. And in the second part, again, 35 minutes, we will be presenting WNTR. In these two parts, you should expect to have an overview of water distribution and collection systems. We will be also talking about package features and capabilities. And at the end of each part, we will have a hands-on tutorial on a simple network. In the third part, which will be the last 10 minutes, we will be having a short open discussion, which you can ask your questions, and we will also go through the questions in the chat. So please, if you have any question while the presenter is speaking, please just drop the question in the chat. So before starting the first part, I would like to give some instructions about the hands-on tutorial. So in this webinar, we'll be using two platforms, Collab and Binder. And for who of you who didn't use Collab and Binder before, they are online platforms that allow you to run Jupyter notebooks without installing anything locally. So we recommend opening these notebooks and following along with the speakers. And again, if you have questions, just drop them in the chat. We also encourage you to download these notebooks and test them offline. And please be aware that there's inactivity period. If you aren't using the window, it will be inactive and you might be disconnected. So please don't panic. If you received a message that you are disconnected, just reinitiate the run by either pressing the play button or refreshing the window. So for the PySWM tutorial, we will be using Collab, and please just copy or write this address in your browser. And once you open it, you will see a GitHub page, which you will have to click on the Intro to PySWM ecosystem link to direct you to the Collab page. And for the WNTR tutorial, we will be using a different platform, Binder. And again, once you write this link in your browser, you will see this notebook. It's called WNTR Basic Tutorial. Just press on this. And please do this right now. I will keep this page for a minute or two so that you can copy these two addresses. And please do this specifically for Binder because sometimes it takes more than 5 minutes to initiate your run. So it's good to have it ready before we start part two. Okay, so let me check if we have Abby here. Oh, sorry.
Yeah, I'm here.
Oh, okay. Welcome, Abby. How are you? So I will, in a minute, I will hand the presentation over to you. I will stop screen and I will also write down these links into the chat so that you can access them later.
I think Meghna already put them in, so.
Okay, that sounds good. Okay, so I will stop sharing. Abby, please feel free to share your screen.
Can you all see my screen?
Yes.
Awesome. Cool. Yeah, so quick note. So most of these Jupyter notebooks are here. I've given some additional links that I'll talk about for some additional resources. I know we have 30 minutes. I'll try to cover as much as I can, but in case I couldn't get to it or for something, most of the notebooks have detailed descriptions, or at least some amount of description on what they cover. So please, you can probably follow them in your own time as well. But if you have any other questions, yeah, feel free to reach out to me. You can just raise an issue on GitHub or email me. Oh, yeah, all of that is completely okay. So I assume you guys probably clicked on this and you are here. Uh, as long as you're signed in into your Google account, you should be able to access. Uh, do let us know in case you're running into any issues. Okay, sweet. So yeah, let's get into it. Uh, so what my main objective for the next 30 minutes is to kind of give an overview of how you can model stormwater systems in Python and also kind of show you the ecosystem of libraries that we've built around PySWM to facilitate uh, either kind of pre-processing data, post-processing data, running new stormwater control algorithms, running new pollutant models, kind of just give you a glimpse of what is possible with PySWM and also give you a brief introduction into PySWM. Then we'll go into slightly more fun stuff about how you can use PySWM to combine your traditional stormwater modeling with any of the machine learning approaches. We'll take a look at like a simple optimization using Bayesian optimization. That'll give you some sense of how you can probably leverage like all the amazing Python um, computation stack like scikit-learn, PyTorch, and combine them with EPSWim to kind of get us to kind of address your own problems. Uh, Quick introduction about me. Uh, I work at Xylem as a data scientist. I develop basically machine learning algorithms for time series prediction, anomaly detection, kind of do some real-time control. I mostly work with clients in North America. My background is in civil engineering. I have a PhD in civil engineering as well, but my focus has been intelligent infrastructure system. So it's kind of my work kind of lies in between machine learning and civil engineering. So where I essentially kind of say, okay, how can I take all the concepts from electrical engineering and apply that to water infrastructure and can help like address like challenging problems like building resilient infrastructure, ensuring how we can better use our existing infrastructure to protect downstream water bodies and things like that. That's enough about me. Okay, so let's get into the stuff. So one thing, if you haven't used Jupyter Notebooks before, all you have to do is you can either press this button or you can do Shift Enter, and it'll Yeah, just trust me, I'm not trying to ship any viruses. So if anything, all of those are related to the authors of these packages. But yeah, once you do shift and enter, it'll install these for you. Note that it doesn't, it's completely on Google Cloud, so it's not installing anything on your browser. So you can feel free to mess around. It's not going to change any of your Python environments. It might take a quick second where it'll install all the dependencies, so we don't have to come back and install it. So we'll first talk about PySWM. I assume you guys are probably familiar with Pandas and Matplotlib. Then I'll introduce each of these additional libraries that kind of extend PySWM capabilities. Okay, so let's see. Most of it seems to be done. Okay. For people who are probably not familiar with PySWM, so what is PySWM? I assume most of you might already know what is EPSWM. What PySWM does is it provides almost a Pythonic interface for EPSWM. So let's say if you probably have seen EPSWM, it has a graphical user interface where you can click, install Storm events, and run the entire simulations. What PySWM enables you to do is do everything you can do in a GUI with Python. So you can kind of write your Python code to trigger simulations, essentially kind of reducing the amount of work you have to do. The other thing, which I think personally is the best part about PySwim, is it lets you stop the simulation midway, change things in the network, and kind of continue the simulation. This is a very powerful feature, and this feature kind of enabled a lot of research into the real-time control of stormwater systems. Um, we'll kind of show you how you can play around with it. The additional thing is PySwim also lets you inject flows. So for example, you want to have a different model that does groundwater and you want that model to inject flows into EPSWM. PySwim gives you the ability to do that. And the other thing is PySwim is really uh, instead of kind of reading binary files and things like that, PySwim gives you the ability to directly convert that into Pandas data frames. So it's really easy for you to run analysis on like hundreds of gigabytes of data pretty fast and generate like calibration curves and things like that. So there's a lot of features that PySwim has. I'm not going to be talking about that all right now, but PySwim has a really good documentation if you go into their page. Um, yeah, so if you go into Python.org, they have really good documentation and stuff which you can easily follow through. They've introduced this new tutorial package that you can read through, kind of play around to get a better sense. But in this webinar, we'll just talk about like a really high level thing, so just so that you get a taste. And also PySwim is completely open source. So you can, if you are interested in contributing, please check out the credits page, see how you can contribute. And it's completely free to use. So you can use it for free for your work, for your research and everything. Sweet. Okay, let's get into this. So I'm just in, so I'll be using something called as PyStorms package. PyStorms is essentially like another additional like part of the PySwim ecosystem. What it does is it provides a collection of stormwater networks that you can use for benchmarking stormwater control algorithms. We'll go into detail about this. The only thing I want you to know is for this example, what it is doing is it's just providing us an input file. So if you see this, it's just showing a path to the input file. And also I'm for people who are not familiar with what an input file is essentially just a representation of the stormwater network as a text format. Like once you open it, you'll see that it's just like, oh, there's a node. This node is connecting to this node. This is what my rainfall is. So you can dig into that, but just know that it is a physical representation of your stormwater network. Now that, okay. Okay, now that we know, now that we have an input file, it's pretty easy to run that. So all you have to do is say PySwim simulation and provide the path to wherever your input file is. And then what we do is we will try to, as we are running the simulation, we will also try to record what is the depth inside a node and what is the flow coming outside from it. So we'll create some empty lists where we can store the data. And what we will do is we'll initialize these objects. What this does is it'll tell PySwim to record these object data. So that's what we're going to do here. So we'll create the simulation, then we'll tell PySwim which ones you should be pulling data for, and then we run the simulation, which is pretty straightforward. You tell this, and then you just have to write a for loop. So when you execute this, it'll run, and it's pretty fast too, and it'll generate these plots. There is a small trick you could do, for instance, if you are saying, okay, I do not want to record anything, I just want to run my simulations. The easy way to do that would be, let's see if we can. Okay. Uh, the easy way, I'll show you that in the bottom. You can run swim execute as well. That way, it'll automatically run the simulation without recording anything, and you can just pass your output files. Now, let's take a look at to see. Now, this is just kind of running simulations. Now, you might be asking, what is the point of this? Because I could do that with my good old graphical user interface. Now, this is where things get exciting. What we want to do here is we want to stop, we want to control how much water comes out from a particular basin. In this scenario, what we have is we have, let me show you, we have, we'll get into this, but we have two basins, and these white dots are basins, and they are flowing downstream into another basin. What we want to do is we want to open the gate, open the valve at the basin based on how much water there is. Now, this is kind of tricky to do in the graphical user interface, like your traditional swim. With PySwim, it's really easy. So all you have to say is similar to the previous example. You have to show what is your input file. You just create some empty list to just log what is happening. You initialize these nodes, you specify which ones you're controlling. In this one, I specify which orifice I'm opening or closing. And then I say, okay, now if my depth is less than certain thing, I want to hold water. But if my depth starts increasing, I'll open the gate. So it's a pretty simple logic, but uh, PyStream enables you to do that. Even though it might seem pretty simple right now, you can probably, for instance, say, oh, instead of doing something simple, I want to have a neural network that looks at what my depth is and then predicts what action to take. All that will become is you just specify, instead of this logic, you can just say, oh, I want to. Yeah, I was trying out some things and that came out to be looking that fun. I do not know how to turn it off, so I've kind of had it on. Uh, so let me remove that later. Okay, control action, for instance, could be equal to neural network predict based on flow. You could do that and you can set the control action, but we don't have to. Yeah, I'm just saying, for instance, if you want to extend that, you could do that. Okay, so let's just run this and see what will happen. Okay, see, what happens is if the depth is greater than 0.10, it'll start, uh, it will start releasing water, but if it is less than that, it'll close the gate, so your depth maintains at 0.10. Now I want to say, okay, now I want to make my depth 0.05, for instance. So you just change that, and you see, again, at 0.05, it maintains it, and if it's greater than that, yeah, it opens it. So it's basically that idea, as PySwim lets you do this. So, and you can, for instance, in this case, you're changing the orifice, you can change pump settings, and you can change a lot of other factors. This is kind of what is one of the really great things about PySwim is the ability to stop the simulation, do something, and then kind of again continue it. So we'll show you how you can use that for like pollutant modeling, for instance. Okay, now again, this is just a very high level introduction. Then you can always go to the tutorials to learn more about it. It'll go into deep about how do you query and all those things like that. Now let's kind of look at now we've kind of seen how you can generally use PySWM. Now, what I want you to also see is what are the different other libraries that you can use in combination with it. So these are kind of a few libraries that I have used extensively, a lot of my colleagues do, and they can be broadly classified into three things. One is your input data, which essentially what you're trying to do is uh, you're trying to for instance, read your text file into a data frame and convert certain things. Let's say what you want to do is increase the depth in every basin that is on one particular street. Rather than manually doing it, you can use SWIM.io to to parse it, create it as a data frame, write code to make that change, and close it so it automatically creates a new input file for you. So it's kind of a nice interface to modify input files. And Swim Pandas is also has a similar interface. The additional thing with Swim.io is it has integration with GeoPandas and plotting, so it's really nice for you to visualize what's happening in your stormwater network. If you go into Swim.io page, it's developed by Adam, who is such a great developer. Yeah, you can generate nice plots like these based on saying, okay, if my flow is greater, I will plot it with like a higher thickness. If my flow is less, I'll plot it with a lower thickness, and you can generate these visualizations for you to better understand how your network is behaving. Um, let's see, let's go back. And Swim Pandas is basically uh, if you remove the visualization, it's basically that. So what this does is it helps you read your input report files into Pandas and create really nice post-processing tools. I'll show you that, but this has really good documentation. So if you're ever interested, yeah, please check out the documentation. It's really thorough. And yeah, it's really useful for post-processing. We found it really useful for large-scale calibrations where you have to process a lot of data and across multiple scenarios. This has been really useful. And then there is a libraries that you can use in during simulations. I've just mentioned PyStorms, which we use to provide us with an input network. If you look at PyStorms, yeah. So PyStorms is something that I developed during my grad school. So the idea is that it's an additional layer on top of PySwim. What this does is it is actually built for prototyping stormwater control algorithms. So instead of having to write a lot of code to control certain things, PyStorms has that code, so you can essentially implement different control algorithms very easily. There's also really a lot of tutorials over here and a bunch of material that you can also follow through. But we'll kind of go over that. And then one of my personal favorites is Storm Reactor, which we developed a while back in collaboration with Brooke. The idea is EPSWIM is really great at doing hydraulic solving. But the problem is the water quality module inside EPSWIM is not that great. It does very few specific things. What this does is essentially uh, lets you decouple those. So what you can do is write your pollutant logic in Python and then interject those pollutants inside Swim so the routing happens. So what happens every step you stop the simulation. Storm Reactor does whatever complex water quality models that you want to run, and then puts that back into Swim. And then it relies on Swim to do the mass balance and everything. So it's a really neat package. I I invite you to guys to check it out and see. It's really useful, and we found that we were able to really do a lot of analysis on, especially on the water quality side with this. Now let's go and see how we can use SwimIO. Okay. Ali, can I go till another 10 minutes? Is that what I have, or?
I think you still have like 10, 15 minutes because I already talked for 5 minutes at the beginning. So
Okay, sounds good. Thank you.
sure.
Let me see if I have questions.
So meanwhile, I am trying to answer as much questions as I can, but we will go
Okay,
through every question at the end so everyone knows. But
okay,
I'm
sweet.
just trying to save some time.
Okay, sweet. Okay. Now let's run these examples. Okay. Now, what we will do is we'll show you how you can use SwimIO to read your input file. So essentially what it does is it reads the input file. In this case, if you remember, this is just providing the path to input file, and you can see it's just kind of reading that as a data frame. So you can kind of, what you could do is you can change these parameters and kind of regenerate another input file, or you can just use them for plotting. So essentially this gives you just a nice interface so that you don't have to parse a text file to understand what's happening. So this is just a really nice, smooth integration into the SWIM input files. And now the cool thing is it also has a lot of plotting features like we talked about. So where you can say is, oh, I want you to draw it. I want you to increase the size based on the amount of max flow, for instance. So in this case, you can see, oh, these are the amount of max flow that's allowed in in each of the pipes. So it will plot the width of the pipe based on the max flow. So you can do really fun visualizations based on that. And you can see these plots here to understand some other additional things about how this is coming. And the other thing, which I kind of alluded to, is the swim pandas. Swim pandas kind of converts your output file into a data frame. So in this case, what we're going to do is just going to run the swim simulation. Now here, I'm not doing anything with the simulation. I just want to run the simulation. So there's an output file that I can read. So that's what this is doing. So you don't have to kind of run something that you've seen here, where you're doing for each time step, you can just directly say, oh, I just want to execute the simulation. So what this does is it just runs the entire simulation and just gives you the output. So let's just run that. Yeah. So once you have run complete, that's a good thing. So if you remember, what we did is this was just the path to input file. And the way Swim does it is Swim will store the output file at the same path. So we'll just replace that here. So what you will see is that you have the same output file here. Now, once you initialize that into a class, what you'll have is you can then read all of this data as a pandas data frame. So you don't have to record it. If you're not interested, you can just say, okay, I'll use this for plotting or any analysis. For example, if you do P2, you'll get all the flows and depth related to P2. And then also it has complete feature parity. So essentially any data that is being stored in the output file, you can just pull it out using Swim Pandas. And once it's in a data frame, everything is easy. So you can easily plot what is happening, study, do some computations on top of it and things like that. Now we talked about, okay, we're not doing a CSTR in this. I should change this. It's just we're doing a first order dynamics. Pardon me for that. Forgot to change that. But you can definitely do a CSTR. So Storm Reactor has a CSTR, which is a continuously stirred tank reactor. It is just a nice water quality module, right? Nice water quality model for wastewater systems. So in this case, what we're doing is we import water quality. So what water quality does is it has implemented a lot of uh, water quality functions like first order reactions, CSTR reactions, nth order reactions. So you don't have to implement them. So it comes with a bunch of good stormwater water quality models that you can directly use, but also you can implement your own things. I'll kind of talk about that at the end. But what you could do here is it's pretty simple. So you specify the input file that you want to play around with. Also note that this input file might not work. You might have to manually add it in because sometimes Google Colab does not take local files, but this file is already here. So if you go to data, it's here. You can manually upload it, or when you're trying locally, you can easily play around with it. Let's see. Yeah, as you see, it does not, yeah, it does not have it. So what you could do, for instance, is you can just upload it here. Let's just do some, yeah, sure. Let's get path, and we can just add the path here. There we go. Sweet. There we go. Nice. Okay, so now that it is running, so you can see here, and as you can see, all the output files and everything is generated here. So we just implemented a first order decay equation, and you can see the pollution went up, and then kind of enter a steady state here. So for instance, if you want to, let's be absurd and do that, you can play it. You lose more reaction, you lose more pollutant. So you can just play around with these. But essentially, what I wanted you to see is how simple it is to implement a different water quality model. You just specify what type of swim element that is, what type of pollutant you want to control, and the method, and then it automatically does it for you. So you don't have to implement most of it. If you go into from reactor, you will see what are the different things. You have a bunch of examples here. What are the different methods that it supports, and how you can also write your own water quality module essentially. Yeah. Um, I know it's kind of been going really fast. I just wanted to give you a rough idea of what is happening. So with the intent that you can go explore all of these on your own time. I've also included a bunch of publications here that kind of extend like what are the packages that we're talking about, like what are the different analyses that we've done and things like that. So I hope you can refer to those. Let me go back to this. I think I have 2 more minutes. I'll just quickly show you one more thing. I'm not going to deep about methodology. I will let you guys dig into the methodology. But what I want to show you is how you can combine a different, completely data-driven methodology with SWIM. So in this case, what we are doing is we're doing something called as Bayesian optimization, which is essentially a black box optimization, which is highly sample efficient. It's a good alternative to genetic algorithms. So what we will do is, you should, yeah. Okay, so I think I have about 2 more minutes. So what this does is we are trying to optimize, we're trying to control a stormwater network so as to bring flows below a certain level. And we want to identify a good control strategy for that. So what it does is we create an objective that says, I want you to maintain all the flows in the basins less than a thing, and it will get penalized. So for instance, the objective function here says if my flows are higher, that is bad. If the flows are lower, that's good. And how we determine this objective function essentially is to say is we run an entire stormwater simulation for a certain action and then see what happens. And then we keep repeating that. So, oh, oh, I don't know why this is okay. And we keep repeating that. And this kind of goes through how you set up that formulation, how you can use PySWM to do that, and how once you run it, you will see how you can combine PySWM with like all of these methodologies to kind of develop really cool solutions for your stormwater challenges. I know that's quite a bit, but here are some examples that you can follow through. This notebook is built such a way, ideally with enough information, so that you should be able to kind of do it on your own. So we have some of the details here, and then I'll quickly show you guys some other notebooks I've included. Here, sorry, that's right here. So we did a similar a workshop, slightly larger version of this at EWRI a couple of years ago. So all of these notebooks are here. You should be able to see. This will go into more detail about how do you run SWIM, how do you run PyStorms, how do you process data and things like that. So feel free to check these out. And I've also included links to PyStorms, where we have some more. I don't know why this is not going. Okay. Where we have another bunch of tutorials to another workshop we did a while back. This talks about specifically how you can do real-time control and shows you different implementations. And we have another couple of notebooks that talk about like different methodologies here. I think Delta has a couple of examples on how you combine PySWM with genetic algorithms. There's one example here about how you can use reinforcement learning. I think I need to update this a bit more, but there's a few more examples and kind of a different, different flavor of tutorials across how you can use Swim with other machine learning libraries. Yeah, again, I know it's quite a lot. The idea is not for you to follow every piece of it. Just get a sense of what is possible, and then kind of explore it on your own. Yeah, I think I ran over 2 minutes, but yeah, that's all I have. Uh, I'm looking forward to all the questions that you have and hope found it a bit interesting. Thanks.
Thank you so much, Abby, for your amazing presentation. I agree with you. This is a lot to get in 35 minutes, but I think you did a very good job in that. So there are some questions, but we will keep this to the end. Just to remind you guys, in case if someone joined after the introduction, I will share my screen for a second. So in the second part, which will start right now, we will be using Binder. So please write this address in your browser. I will also share this with you in the Zoom chat. And once you do this, you will see this notebook, this on it. And please do this as soon as you can because it takes 5 minutes for this platform to initiate the run. And yeah, I think we can direct the presentation to Kirk and John.
Thank you. Hopefully Kirk's still on to share his screen. Looks that. All right. Thank you,
Yeah,
Kirk.
looks good. Okay.
I am starting to see it.
Is that coming across?
I'm not seeing it yet. Ollie, do you see it?
No, it's still showing that you started to share your screen, but nothing yet.
There we
Yes.
go.
That
Okay.
one? Okay.
Yeah.
Okay.
Thank you. So, I'm Jon Burkhardt, and I will be kicking things off, which will probably give you enough time to let the binder link load up. I'm here to talk about the winter and other related open source software tools. You can go to the next slide, Kirk. So again, my name is Jon Burkhardt, and I'm going to hand it over to Kirk for the actual demo. Next slide. And I just want to acknowledge all of the other people that went into making these slides when it was initially presented in a longer form for WDSA CCWI earlier this year. And next slide. So we've already kind of done the intros. I'm going to go over the background and overview of Winter and some of the related projects, and then turn it over to Kirk for the tutorial. Those are some links that are related to what we'll be talking about. So next slide, Kirk. So we started looking at this because we recognized that water distribution systems suffer a variety of disruptions. The WDSA community as a whole had recognized this over the years, and it starts from something as simple as aging infrastructure and changes in supply and demand, which are common over the life of a system. But more recently, we also wanted to look at things related to the damage from natural disasters. Many of you may have heard about the hurricanes recently in the southern U.S. Landslides, land subsidence, floods, wildfires, winter storms, earthquakes, all of these can cause, damage that will change the water distribution system. More recently, we've also been interested in saltwater intrusion. And so really thinking about coastal communities where, either intermittent or persistent flooding is causing salt water to get into the groundwater, which could impact the distribution system. Contamination and water quality issues are very relevant to systems, and then cyber and terrorist attacks. So looking at intentional attacks on the system. Next slide. So if we look at the figure, we see what's called the resilience trapezoid. And so we can think about the goal of a resilient system is to minimize the magnitude or how far the system changes, or the scale of that change, and also the duration of that disruption. So how long the system remains in that disturbed state. And so if we can do anything to either prepare for, harden the system, or change the system to allow for more interconnectedness or other activities, or again, prepare in the sense to have materials on hand to, basically be attacking those repairs right away with parts, and really prioritizing critical infrastructure, we can make a more resilient system over time. Next slide. So EPA has been working on various aspects of this for many years, and so it all starts with EPA Net, which you're probably all aware of. It is the sort of core feature for all of this. It serves as the hydraulic and basic water quality engine for a lot of different analyses. EPA Net MSX, or the multi-species modeling extension, was recently updated. It added some features, but it allows for multi-species contaminant modeling. It's also being integrated into Winter, which we're going to talk about more. The TIVA Spot tool is a threat evaluation and sensor placement tool that some of you may have worked on or used. Canary is sort of the odd tool out here. It's actually more of a data analytics tool, but as we think about things like digital twins and other areas of research, Canary is just looking at trying to monitor or capture when a change is realistic or important to a system. The Water Security Toolkit, or WIST, is looking at response action optimization. Things like flushing, booster chlorination, source inversion, and backtracking are present in that. And then we also have looked at real-time modeling with the EPA Net RTX libraries that were developed a number of years ago. Next slide. So the sort of nexus of this has been to develop, or the development of Winter, or the Water Network Tool for Resilience. It is an open source Python tool, and it's designed to answer a lot of the questions and more. It provides a lot of flexibility for answering these things. But the key questions are, things like how long can a system continue to operate or provide water to customers during a disaster? It's really a failure state model. And so prior to the changes with EPA Net recently, with introducing the pressure dependent demand, you couldn't model a system that was in a failed state. And so that's part of the impetus for why we developed Winter. But the other questions are, how many people will be impacted? So, looking at metrics for that, which are the critical infrastructure or functions that will be impacted, and how big are those impacts? What's the best response in the immediate aftermath, or even the long-term aftermath of a disaster? And then which components, could be or should be hardened to minimize the future disruptions. Next slide. So the key takeaway from this slide is this is being used. It's on PyPy and Conda Forge for download. It's had at least 20 software releases. I think we're working up to a new one. A lot of contributors. So if you're interested in contributing, feel free to fork Winter and contribute, and we'll be happy to consider pull requests and issues related to it. But it's been used worldwide, so it's a great community, and thank you for those of you who are using this now or considering it. Next slide. So here again, this is just some of the great work that's being done using winter. Things like leak detection, cyber resilience, earthquake resilience, and so on. I won't read the whole list, but a lot of really terrific work. And I think the bottom is really important, and many, many more. So if you are doing work and publishing, using winter, it's great to see all these great ways of trying to understand water resilience and other problems around water distribution systems. Next slide. This is just a short list of what we've done at EPA. So we published, the initial work was an earthquake study. We've looked at power outages, contaminated water source, a loss of water source, environmental justice concerns, so sort of looking at a GIS component. A recent paper was also published on landslides, so that look for that in journals in the future. And we have a summary as well that we can certainly share with people that are interested. Next slide. And so I just want to leave you with this thought as I hand it over to Kirk, but this is really about the ecosystem. Winter has a lot of different data formats, as Abhi talked about for PySWM. The sort of the core of this is obviously the winter network model. This talks to the EPANet IMP file, but you can also work with JSONs, dictionaries, CSV files, Panda data frames, GeoPandas, GeoJSONs, and so forth. And it also just taps into tools like NetworkX for graph theory analysis and other things. So it's really just opening up the EPANet modeling to the bigger ecosystem of the Python ecosystem. So with that, I'll turn it over to Kirk, and he'll walk through the demo.
Okay, yeah, thanks, John. So while I transition over, I'll leave this slide up in case you haven't made it to the webinar binder. And I'm just going to make sure that everything is still working on my loaded copy. It looks like it is. So yeah, let me switch my share over to the tutorial. Okay, are we seeing the tutorial now?
It's still loading.
Still loading. Okay, well, last time when I stopped sharing and then I tried it again, that's when it actually worked. So we'll see if that does it.
Yeah,
okay, I guess you just got to do it twice.
Yeah.
Okay, so yeah, that was a great introduction to winter and kind of the ecosystem by John. So I'm Kirk. I'm at Sandia National Labs. One of the things I do there is work with winter, but I also maintain it as a software. So in this tutorial, we're going to just mostly focus on that water network model that John made reference to, which is really the core object of winter. But I also want to get into some of the actual simulation. So the two sections of this very long and comprehensive tutorial we're going to focus on are the water network model and simulation. There's a lot of other good stuff in here that I won't get to cover in the allotted time, but I do encourage you to go through it on your own, as well as some of the other resources that I'll be pointing out near the end of the tutorial. Okay, so starting off, just our imports, right? We depend on a couple of pretty standard scientific computing packages like NumPy, SciPy, NetworkX, GeoPandas, and Matplotlib. So if you're on the binder, you'll want to run this line, which will actually install those. I did that ahead of time, so all I have to do is import these. The next cell will create a couple of directories to hold our results. And before we jump into the water network model, there's a note about units. So in winter, we use all SI units. So whenever you're interacting with Winter, be sure to use units. If you're unsure, sorry, SI units. If you're unsure, we do have a page about units in our documentation that really goes through it in detail. So with that out of the way, let's jump into the water network model. So Winter is primarily an object-oriented package. All of our data is stored in objects, and the principal object is the water network model. You can build this up from scratch, but typically you will be making a water network by ingesting a .imp file, which is the EPANet text file format for storing water distribution system information. So here in this first cell, we'll just create a water network model called WN by passing in the path to the IMP file. We can take a look at the basic description of the model by running the describe method. This gives us an overview of the nodes, links, patterns, curves, sources, and controls in the network. Each of these sections we're going to go through in a little more detail. We can also list in this next cell all of the properties and methods associated with the water network model. So as you can see, there's a lot of information to access and a lot of things you can do with the water network. Of course, we can't go through all of them, but we will be touching on a portion of those in the rest of the notebook. Very useful function for Winter is the plot network function in our graphics module. So here we're just showing the nodes and links, the topology of that network. But there's a lot of extra functionality on plot network that we'll see a little bit of throughout the rest of the notebook. So jumping into nodes. So node objects are how we define junctions, tanks, and reservoirs. We can get a list of all nodes in the network by accessing node name list, that property. And you can see there's quite a few. If we want to just look at a specific kind of node like tanks, we can use tank name list. And that shows that there are 3 tanks in the model, 1, 2, and 3. To actually access a tank object, we use the getNode method and pass in the name, which in this case for tank 1 is just 1. And we can print out a preview of what that looks like. So the tank object contains some information about the tank, like elevation, min and max levels, diameter, and some others. You can also look at all of the properties and methods for the tank. Again, there's quite a few of them. Some of that is just inherent information to the tank, and some of it captures active simulation results. For the properties like max level, we can change those just with ordinary Python assignment. So for tank.maxLevel, we can set that to 10. We can see that before it was 9.7, and afterwards we now see that we successfully changed it to 10. To add new junctions, a new junction to the model, we use the add junction. For tanks, it would be add tanks, or for reservoirs, it would be add reservoirs. But you pass in the name you want for that junction, as well as some of the basic attributes you want assigned to that junction. And so we can see after running this code that our junction name list now displays that new junction at the end. And we can use remove node to get rid of any node we don't want by passing in that name. OK, so now we'll jump over to links. So links are the object we use to define pipes, pumps, and valves. So we'll kind of go through an analogous set of cells here. Using link name list, we can get a list of all of the links in the network. And we can specify that for just head pumps using head pump name list. And we see that there are 2 of them. A useful function for links is this get links for node method. That allows you to pass in a specific node, and it will return all of the connected links. So we see for node 229, there are 3 different links attached to it. To actually access a link object, we use getLink and pass the name, just like for getNode. And here we'll get a pipe, and we can see some of its information. So the name of the pipe is 105, and its start node is 101, end node is 105, and we see its length, diameter, roughness, and some other properties. We can get a full list of those properties and methods by running this cell. And we can modify the attributes just as we did before for the tank. In this case, we'll set the diameter to 10. So you can see previously it was 0.3, and now we've updated it to 10. The add pipe method is how we can add a new pipe to the network. So we give it a name as well as its start node name and end node name. So if these nodes don't already exist in the network, you'll need to add those first. If you're building it from scratch, for example, the nodes already have to exist. And then things like length, diameter, and roughness as well get passed in. So we see that the new pipe was added, and we can use remove link to remove that at the end. OK, so that covers kind of the basic topology of the network, the nodes, and the links. So in this next section, we're going to take a closer look at junctions, which are kind of be thought of as ordinary nodes in the network. And these are where demands are held. So a junction might be in the middle of a residential street, and you might attach demands from houses in that area to the junction. And so the way we store that is in this demand time series list property of a junction. And each element of that list is a time series object that contains a base value, a pattern, and a category. And these are used to determine what the demand is at each time step. So in the next couple of cells, we'll take a closer look at demand. We can use in the winter metrics module the expected demand function to actually compute what those demands are going to be across the nodes and across time. So we see the columns are junction names here, and our rows are time steps, hourly time steps. And we can see how that demand changes over time. Some nodes don't have any demand. If we want a higher level aggregation of expected demand, we can use the average expected demand function, which averages that over time. So we can see the value for the first couple of nodes here. And then if we pass in this average expected demand, I believe this is a pandas series, into the node attribute option for plot network, we can actually see those values distributed across the network. So this lets us identify things like demand hotspots up here in the northern part of the network. It also looks like there's one down here. Additionally, right, if we wanted to identify junctions with zero demand, we can filter that average expected demand series, just looking for the values that are 0. And once we get the list of those junctions that have 0 demand, we can pass that into the node attribute to highlight where those are. So here in red are the junctions with no demand. To actually get into editing and modifying demands, we can start by grabbing a specific junction and printing out its demand time series list. So here that is for junction 15. We see that there's a single time series in that list. There's the base value and the pattern name, and it currently has no category. So the pattern name is just a name. To actually access that pattern, we have to fetch it using the getPattern method on the water network. And here we see the name of that pattern as well as the multipliers, which are used in conjunction with the base value to determine what the actual demand at each time step is going to be. I believe we got 24 of them here, so this is just giving us, right, our daily kind of disaggregation of demand. Okay, to actually perform modifications, right, here we're accessing that first element of the time series list. So this is a time series object, and we can modify its base value by just accessing it and setting it to some value. We can also add a new pattern to the network using add pattern, where we give it a name and then we give it that set of multipliers. And after we add that to the network, we can assign the pattern name to instead point to this new pattern. And so we'll run all of that. And we can see now that those updates have been made. The base value has changed to 005.005 and the pattern name to new. We can also just add an entirely new demand to the junction using the add demand function. So here we need to pass the base value as well as the pattern name that you want it to reference. And optionally, you could also pass in a category. So let's take a look at that. OK, and now we see that there is a second time series added to the list. Great. So we might want to see how all these modifications changed what that demand over time looks like. So we can fetch the expected demand again after making those modifications, and we can plot the original and the new at that junction 15 we've been looking at. OK, so in blue, that's going to be the original demand over time for junction 15, and the orange shows what it is after our modifications. So it's a little more complicated now that we've added a second demand to the junction. OK, so that covers demands and patterns. Next, we're going to look at curves. So curves are used to define pump head curves, tank volume curves, and pump efficiency curves. So the next couple of cells will show us some examples of accessing and modifying that kind of data for curves. So in this first example, we'll look at plotting the pump curve for a pump. So we'll grab pump 10 and use the Winter graphics function plot pump curve. And this shows us in orange the points that actually define that curve, as well as in the blue dashed line, the polynomial interpolation of those points. And we can access those points directly by first getting the name of the pump curve, and then getting the curve using that name through the getCurve method. And here we print out the 3 points. These match up with the 3 you see here. We can modify the points on the curve by just setting it to another list of tuples of 2 values. So here we're just going to change it to have a single point, and we can assign that and then plot the pump curve again, and now we just have that single value. Next, we're going to look at tank curves. So we'll add a new tank or a new curve called new tank curve. And we're going to specify that it's a volume curve to be used with tanks. And then we just have to provide all the points that make up the curve. We'll grab one of the tanks, tank number 2, and we'll assign its volume curve name to the curve we just created. And we'll use the plot tank volume curve function to take a look at it. So in this first plot on the left, we have the actual points we just defined, as well as the interpolation. We can see the min and max values set on that tank. And what I think is really interesting to look at is you give some arbitrary curve, and you can look at the actual profile of the shape of that tank that would correspond to this volume curve. So you can imagine taking a radial cross-section of the tank. This is what it would look like. And we also see those min and max levels plotted as well. OK, so the last section we're going to cover for the water network model is controls. So controls are how we basically control the operation of things like pipes, pumps, and valves over the course of a simulation. So we can get a list of all of the controls in the network by using control name lists. There's 18 of them. We can iterate through all of those controls and actually print out its contents or a description of its contents. So each control is made up of a condition and an action. So if some condition, then some action happens. And it also comes with a priority, which is used to reconcile any disagreements between controls. So the higher priority is taken. Let's look at a specific control in a little more detail. So this is control 18. So its condition is when a tank 1, has a level go above a certain point. Then the action is to open a pipe, right? So you can imagine, right, if you only want a tank emptying when it's at a certain level, right, this is how you would encode that sort of control. So here we see that it has a priority of 3. If we wanted to update that, we can use the update priority method and set that to 1. Note that this is a little different from how properties have been updated in the past, right? Instead of like control.priority equals 1, you do want to go through this method. I think you'll get an error if you try to do it the other way. So we can see that the priority has been updated correctly. Next, we'll look at actually creating a control from scratch. So here, we'll fetch a pump named 10, and we'll define an action, control action of opening or setting the status of the pump to 1. So that's our action. The condition will be a sim time condition, and that's when simulation time of the network is equal to 121. And we combine those two into an actual control by instantiating the new control object with that condition and action, giving it a name, and then adding that control to the water network. And we'll see when we print out the control name list, there's our new control. And we can remove it using remove control and passing that name in. OK, so that's going to conclude the water network part of the tutorial. There are some other sections on querying, coordinates, loops and generators, pipe breaks and leaks. But I do want to skip ahead to the simulations. Ali, what's the time looking like?
I think we have I think we have like 7-10 minutes.
Okay, cool. That's plenty of time. So yeah, this last section we'll get into actually how you start running simulations. So Winter contains 2 simulators, an EPA net simulator and a winter simulator. So the EPA net simulator, actually, the way that works is you convert your water network model and all of its contents into an IMP file, and then you pass that off to actual EPA net binaries, which will run the simulation and then pass the results back to Winter. The Winter simulator, is actually built into Winter with Python and C++. And so that can run totally independent of EPA net. So we're going to start by reloading that water network from since we made some changes to it in the last section. And the way you control how the simulation is carried out is through this options, water network options interface. So if we just print that out, you just see a whole lot of different options that we can't go through all of them, but I will highlight a couple of important ones. So the options are organized under a couple of different categories. One of them is the time options. So for example, we have the duration of the simulation. That's going to be in seconds, right, using those SI units. So we take 4 days times 24 hours times 3,600 seconds to convert 4 days to seconds. If we print this out, you can see that we've updated our duration here, and we can also get a peek at what these other time options are. So you have like a hydraulic time step, a quality time step, and a couple of other options you might want to play with. Additionally, there are hydraulic options. So this is how you actually change the type of demand model, right, between to change it to like pressure dependent hydraulic analysis. And if you do that, you'll want to pass in a required and minimum pressure as well. So when we do that, we can print out the options and see those updates. The demand model says PDA, but that's equivalent to PDD in winter, so it did work correctly. And we can see the minimum pressure and required pressure showed up as expected. And yeah, there's a couple of other options, like for example, IMP file units. Right, this if you're using the EPA net simulator, this will convert all the internal winter units to whatever you want it to be for EPA net. Winter takes care of that automatically. So as long as everything is correctly in SI units for winter, the conversion should go smoothly. OK, so those are the settings. To actually run the simulators, it's very simple. First, you instantiate either the EPA net or winter simulator by passing whichever water network you want to simulate into the constructor. And then it's just a matter of running this run sim method, which will return the results of that simulation. So the interface is the same for EPA net and winter. So we'll run both of those and take a look at those results. So the results object holds everything you would want to know about the simulation. It's organized into node results and node result and link results. So for node results, we have demand, head, pressure, and quality. If you access this, yeah, you can see in this next cell, this is how you would access a particular key there. For links, we have quality, flow rate, velocity, head loss, the status, setting, friction factor, and reaction rate. And to actually view these results, we can access the pressure and take a look at the first couple of values, first couple of time steps. So this is showing across all of the nodes at each time step what the pressure is. So something you might be wondering, if there's two simulators, how do they compare? So you can actually compare the pressure results between the two simulators, the EPA net and winter, and look at the difference, the maximum difference across all those nodes over time. So note that the y-axis is in meters of head. So these values are extremely small. But there are some slight numerical instability differences that can occur. Overall, for most simulations, you won't see big differences between winter and EPA net. But there are some differences between the two simulators and some limitations that are expanded on in our documentation. Last couple of plots here I want to show off. We can look at tank levels over the simulation. So we see our 3 tanks and some periodic daily behavior. We can also look at pump flow rates. Again, seeing that periodic behavior, daily behavior. And finally, we can extract the nodal pressures at a particular, nodal pressures at a particular time point, in this case 5 hours into the simulation. And we can pass those values into the plot network function to actually see the geospatial distribution of pressure at that time. There you can see some high pressures up at the top, and then pressure kind of slowly decreasing down as you get through the network. Somewhat of a gradient there. OK, so that is kind of a basic how to both interface with the water network model object and how to run some simulations. Winter is so much more than that. We really emphasize, like Jon was saying, the resilience aspects. So in a lot of our other tutorials and scripts and resources, we really go into that in more detail. Even in this notebook, we do get into some resilience metrics. So certainly check those out. In this binder, we have another tutorial called the geospatial tutorial. And it goes into detail on how to interact with geospatial data and the various geospatial capabilities of winter. I also want to call out our documentation. It's very thorough. Our user guide is very helpful. there's a lot of detail on how to set up different analyses and all sorts of aspects of the package. We have a complete API documentation if you're looking to get into the details. Additionally, on our GitHub, we have a lot more examples you can check out. Right? We have a couple of different scripts for different kinds of analyses. We have a getting started script as well to help introduce you to the usage of Winter. And then in this demos folder, we have the basic demo and geospatial demo we just saw, as well as a couple of others. So hopefully this was helpful as an introduction to Winter as a software. There's a lot of resources out there, like I just mentioned. So definitely look into those if you want to learn more. With that, I think I'll hand it over to Ollie. Yeah, thanks.
Thank you so much, Kirk. Thank you, John, for your amazing presentation. So we have around 15 minutes. So let me share my screen with you. Because we got a lot of questions, very nice questions in the chat. I believe Abby already answered the PySWM questions, but I selected 3 of them. I believe they are the most important ones, just in case anyone else has the same question. So the first question was, can we install PySWM locally? So are you still here, Abby, or do you want me to answer? Yeah, okay.
No. Yeah, so you can install PySWM like you do any Python library. It runs on Mac, Windows, and Linux. So yeah, you should be able to just install it.
So the second question, does PyStorms model pollutants like DO, BOD, H2S, which are water temperature dependent?
So
I know the answer for this question is very long, I see, but if you can, give a very brief answer to that.
So the thing is, PyStorms is a different package. It does it's effectively for stormwater control. Like it says, I want to develop a stormwater control algorithm. So how do I test my algorithm? That's kind of what the question PyStorms answers. Storm reactor. I know there's a lot of storm words here and there, so I can understand. Storm reactor is for the pollutant modeling, and it does handle that. So essentially, if you can, but the thing is, SWIM does not have any temperature dependent, as far as I know. So you might have to implement that in Storm Reactor, but we do definitely have the code to do that. You can query the temperature and kind of change these variables based on that. But yes, you should be able to do that. Ali, do you want me to answer the next question as well?
Yes, please.
Okay, yeah. So I think the fundamental thing about PySWM is it's not re-implementing anything. So the idea is for you to use exactly the same things under EPSWM. The advantage there is EPSWM is vetted by EPA, and it has in case you're doing any reporting to government agencies, they want you to run EPSWM. So what PySWM does is it just calls whatever C functions that are in EPSWM. So it's exactly the same thing. But when you make modifications to Storm Reactor and things like that, it adds some additional functionality, but none of the core solvers, none of them are re-implemented in PySWM.
Thank you so much, Abby. So the second part of questions are related to Winter. So John and Kirk, can you please answer these nice questions?
Yeah, I'll start. So the top one is the Winter only compatible with EPANet. Can it take SWIM inputs as well? So we are looking at trying to integrate SWIM and Winter together. So that's more to come. I won't, but it's primarily at the moment just looking at EPANet IMP files, and we're working on integrating the MSX capabilities as well. And so there's an active pull request for that. I don't know, Kirk, if you wanted to add anything to that one.
Yeah, there is an open pull request for some SWIM capabilities as kind of like a sub package of Winter. Yeah, it's still in its early phases. So even when this initial poll gets through, I wouldn't expect it to be as sophisticated as the rest of winter. But yeah, I mean, look out in the next couple of months. Hopefully, we'll get it pulled in some amount of swim capability.
So I have a follow-up question regarding this. You mentioned that there's an ongoing work to add the swim capability, but I think we already have PySWM, right?
Yeah, so we are looking at using, not reinventing the wheel there, but we have metrics and things like that for the resilience that are already built into winter. So that's part of the area that we want to leverage. So yeah, it's not going to be reinventing things like PySWM, and so I think the Sandia folks are working with the developers of PySWM and other tools so that their dependencies. So yeah, it's not going to be a complete, from the ground up like winter was, build.
Yep.
So I'll answer. It looks like the next couple questions are about, the EPA net versus winter simulators and pressure dependence. And so, EPA net is faster because it's compiled C code. Winter is a combination of Python and C code, and so that's part of it. So that's the primary reason why the EPA net solver is faster. The winter simulator, so further apart from the simulating leaks, what's the advantage of the winter simulator? And so winter is going to be breaking, changing the system dynamically as part of the simulation. But at least one thing that comes to mind is that EPA net for the pressure dependence only allows for a global pressure dependent, as Kirk highlighted, minimum and required pressure, where the winter simulator actually can allow that to be node specific. And so particularly I'm using the winter solver for some premise plumbing work with node specific pressure dependence. And I think that so the next question relates to the pressure dependence. I think that it's using the exact same algorithm, which is sort of was shown by Wagner previously. So I don't think that there's any difference between them. It's just like I said, one's in fully C and the other one's partially C or C++ and Python.
Yeah, I can add on to that a little, John.
Yep.
So a big, I would say the big difference, and kind of you probably have the question, why, if they have the same algorithm, why have the Python C++ version? The big motivation for that is that the winter custom simulators built on this algebraic modeling language that allows for kind of generalization of the the simulator's code. So for example, we've used that to add leaks into the equations of the simulation. But there is a section on this under advanced simulation techniques on the documentation that kind of gives some examples on how, say you find some research paper or you have some research of your own where you want to slightly modify these equations and see what happens. Winter gives a capability for doing that, and I think in a pretty convenient way, because I think without it, you'd have to build everything from scratch. So right now, I think the leaks are the only thing that we've expanded on using that. But for advanced, simulation, if you have some, pretty interesting ideas like that, that would be a capability Winter would allow for.
So we also have a question about the units. I believe, Kirk, you already mentioned that only SI units can be used.
Yeah, for Winter, yeah, SI units. But when it gets passed to EPA net, you can specify kind of the EPA net unit type you want, and it will convert it. So if you write the IMP file out and open an EPA net, you'll get whatever units you want. But yeah, it should be in, I guess, meters cubed per second for any flow values.
Yeah.
In Winter.
And there's this question, can the results be saved partially? And can the simulation be paused to change something and then resume it? I believe yes. What do you think?
So yeah, I think we have some capabilities for this, but it's not fully fleshed out to do like stepwise simulation. Certainly, if you pass something to EPA net and some exception gets raised in that binary, like you don't get anything back. You just get that error code. So no partial results there. John, feel free to hop in. I'm trying to think of what is actively available.
Yeah, I think you'd have to build or expand on the step-by-step, simulation. Yeah, EPA net certainly doesn't, because it's just calling the engine, so you'll just get the result back. If you do set up the simulation to run it step-by-step, you could keep track of it, but you'd probably really slow down your simulation. So that'd be the trade-off, because you're having to call a Pythonic function and then get the save the results and so on. It may be worth it, but that's also something we value inputs. So if that's an issue that you want to raise, we can certainly think about it as a team and see where it would go.
Yeah, so I have also a question. I think you already answered this while answering the other questions about if even at MSX is supported in winter, but it seems like it's ongoing work, right?
Yeah, it's pretty close. You can work with the pull request version. We're also working to create some Jupyter notebooks like Kirk showed that would walk through some of the MSX capabilities, building from. We're looking at adding libraries, so you would have pre-built versions that have already been published, other things like that, and walking through those examples. So it's very much in progress, but we're definitely working to add that.
Yeah, this would be great. So we have two final questions. We have 2 more minutes, so hopefully we can answer them. So can winter more errors if a physical wrong control operation is assigned to pump or tank?
I don't know, Kirk. Do you know if winter would warn if there's a problem with the control or something?
Yeah, I'm just trying to think of what a physically wrong control operation is assigned. Yeah, like I guess for example, like if it's if you have some control triggered by a tank level being higher than what is possible, that would be an example. I want to say yes that we would raise an error, but I can't recall ever encountering something like that, so I couldn't be sure. That's a good question.
I think that would be a great feature kind of request, but that could certainly be a lot of work. I think if it tries to do something that Python won't let it may at least throw a Python error. But like Kirk described, if you just say if the pipe or the tank level is above 20, but the tank never gets above 10, do something. It's not verification, or it won't check against the item itself. But that's something that could potentially be added. But there would be a lot of thought. So yeah, it's if you want to contribute those kind of ideas, or even the code that would do it, that would certainly be a nice feature.
Yeah, so I think Abby already answered the multiprocessing capability of PySWM, and the answer here is yes. Yeah.
That's a simple answer, Avi. You got
Yeah.
away easy on that one.
No, it's just that people have asked me that question so many times, so I just wrote something up for it.
Yeah, personally, I had I had to do this maybe 2 years ago. I think even before you did this, Abby. So it's a very nice tool to have actually, specifically if you are working on optimization. because eventually you would have to run like a lot of simulations.
Yeah.
So yeah, I think we are done. Thank you so much, everyone. It's already 1:30, so just in case if you have more questions, please feel free to stay in. But other than this, you are free to leave. We will definitely let you know on our LinkedIn channel about our future webinars. And finally, I would like to thank all our speakers for their amazing presentations today. Thank you all.
Thank you.